All right, the last thing we did when we were talking about modules of PIDs, uh, I sort of repeated the decomposition we have from, the fundamental theorem of finitely generated big groups, and then, more generally, modules over PID. So here, I'm going to give you a couple of theorems that talk about how to decompose a single linear transformation, and then we're going to tie it all together. We'll do a lot of examples. So let's start with theorem. Suppose we have a linear transformation phi transformation then V is phi cyclic with minimal polynomial. Minimal polynomial Q if and only if the dimension of V is R. And there exists a basis for E such that the matrix of phi with respect to this basis is right. And I like to write it in this form, which is kind of unfortunate because 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0. And finally, and here, E, so my basis is, this is phi cyclic. Now, yes.
Okay, I think that thing is X, but it doesn't really, not very important. What's the question to X? I never saw the transpose in linear algebra.
That's what I was going to say. So this is using vector multiplication from you multiply by the matrix on the right, right? Because, for example, if you look at the this matrix C, if it represents B by 1, 0, 0, then BC is equal to matrix 0, 1, 0, and so forth, so on, right? And finally, which is B of P. And finally, what happens is if you have, zero, 0, 0, 0, 1 times C, this is equal to, and this is where this comes from. This is, minus A0 minus A1 minus AR. But of course, this is set up to be exactly what it needs to be, right? So he's right. If you want to do column, if you want to multiply the matrix with a column on the right, you'd have to take the transpose of this. But, you know, this is the way that I've written all the stuff in the notes. So I apologize for that. If you like doing column vector multiplication with column vectors on the right, you'll have to do the transpose. It's 6, 1, and a half dozen together. Now this is what I call a block. And it's going to be used for what I call the primary, or the rational canonical form, the primary rational canonical form. So these blocks are going to be used as our elementary divisors or our invariant factors, depending on which canonical form we're going to use. If all eigenvalues are in field K, then we have following corollary. Let P from E to E be a linear transformation. Then E is phi cyclic and has minimal polynomial. Minimal polynomial. X minus lambda to the R. If and only if mention is to R, and as a matrix as a basis for which the matrix of phi is lambda 1, 0, 0, lambda 1, 0, 0, 0. Lambda 1, 0, 0. And when the matrix takes this form, it's just called an elementary Jordan block. Let me prove the corollary. Um, um, but or let pitchfork be phi minus lambda I, then Q, this polynomial, is the minimal polynomial phi if and only if x to the r is minimal polynomial. And that's all you need, because notice, if you have minimal polynomial x to the r, and you look back at this rational canonical form, if the minimal polynomial is x to r, this is just, this last row is a row of zeros. So this is the matrix filled with all zeros, right? Except you've got ones on the super diagonal, right? Now reverse this and notice that phi is, and that's where you get the lambdas down the diagonal. All right, so there you go. Okay. Okay, any questions? All right, now it's example time, and I'm gonna pick this apart. Now, the first thing I'm gonna do is I'm gonna cheat a little. So we'll take small steps. Example. Let's suppose that I have a linear transformation with invariant factors I want to try to be field independent as much as I can with invariant factors. Well, how will start? Let's suppose my invariant factors look like this. Yeah, I'm gonna write this out. X squared plus 1 squared. Times x minus 2 squared. And let me multiply that out for you. This is x to the 6 minus 4x5 plus 6x4 minus 8x cubed plus 9x squared minus 4x. Okay, and that's one of our invariant factors, and the other one is x squared plus 1 x minus, which is x cubed minus 2x squared plus x minus 2. And okay, so I walk up Mount Sinai and I come down having been given these 3 invariant factors to pass on to my people. Now, the one thing that you might not like about this example is, okay, you know, some higher power gave you these, how do you figure them out in the first place? Well, we'll get to that. But let's just suppose for now that I know that these are my invariant factors. So let's put together a rational canonical form. So here, what we have is we have 3 invariant factors. That means I'm going to have 3 blocks. And my blocks are going to look like just those primitive blocks I wrote down. And it doesn't matter what order the blocks are in, because it's all the same thing with similarity. So my rational canonical form. Okay, let's do this block first. By the way, what should the total size of the matrix be? Yes, you're right, it's 11, right? So there should be a block of size 6, one of size 3, and one of size 2. Right? So this should be an 11 by 11 matrix. And maybe you will forgive me because every entry that I don't write of the 121 entries will be a 0. Okay. So the first thing I'm going to do is I'm going to put the 6th block. And finally, these in reverse, -4, 4, -9, 8, -6, 4. Everybody okay with it? First block. Now I get a 3 by 3 block. Have to pick up the diagonal down from this. Whoops. And finally, I guess I get 2 -1, 2. And finally, I get this last little 2 block here. Now, fill all the blank entries with 0. And there's your rational canonical form for this matrix, right? And of course, look, this is a sparse matrix in the sense that there's not a whole lot of non-zero entries in this matrix. And the form is kind of nice to handle, so it's usually a much better situation. Now, just like there was a invariant factor decomposition and a elementary divisor decomposition, then there's a rational canonical form. This is invariant factor. And corresponding to the elementary divisors, we have a what's called primary rational. And this is elementary prime. Okay, well, for us to do this, I guess I need to find out what the elementary divisors here are. So it's also been 11 by 11 matrix, so we can kind of gut check this as we go along. What are my elementary divisors here? What's that? Well, so what we're looking for is the prime powers, right, that divide this, right? So I get so this squared, and then this, and then this. And what else do I get? Well, I get 4, 6, 8, 10, 11. Good. So there are that's an exhaustive list of my elementary divisors. These are the prime powers that divide the polynomial, right? Somebody tell me why the distinction that we made that we're over the field Q is important. So for example, what would happen if we were over the complex numbers?
You would factor x2 plus 1.
That's right. You would have to factor x2 plus 1 because over the complex numbers, this is not a prime power anymore. Right, we'd have to break that down further. We'll look at that in a minute. But here we're still over the rationals. And so for the invariant factor decomposition, or I'm sorry, for the primary rational, which is the elementary divisor, well, let's just go through the blocks again. None of the blocks will be, so we had a 6, a 3, and a 2. Here we're gonna have more blocks and they're smaller. Right, we're gonna have a 4 block. And then we'll see what we got here. -1, -2, 0. So that takes care of this big one. Then I have 2 smaller 2 blocks for this. And finally, I have a 2 block and a 1 block. So this one, 0, 1, -4, 4, and just 2. Fill the rest of that up with zeros, and there you go. So more blocks, but on the other hand, it doesn't spread out as much. So if I give you the invariant factors, you should be able to get the elementary divisors and vice versa, just like we did last time. And you should be able to do this. Let's take one more look here. Over the complex numbers, what about over the complex numbers? Well, I mean, I just gave you the invariant factors, right? And so the invariant factors are still good to go, right? So if I were doing this matrix of the complex numbers, my rational canonical form, same, nothing changes, right? But when I want to go to primary rational canonical form, notice that so that's the way that you actually break down. Of course, over the complex numbers, there are no irreducible polynomials of degree bigger than 1. So we've got that going on. Then so my elementary divisor. My elementary divisor should be this. Let's kind of go through it here. What Dorcas and Dorcas. So my original invariant factor for this. Is that right? That's right. I think I'm ready for the 4, 6. Yep.
Second was x squared minus 1x minus 2.
You're right. Thank you, thank you. Good, thank you. So let's pull out the elementary divisors here. And I'll do this in prime powers. Let's see, I guess I've got x plus I squared, which is x squared plus 2i x minus 1. And then I've got x plus I and x plus I. Okay, that's pulling me from x plus I out of all of these. All right. And I've got something similar for x minus I. And the 2, actually the field doesn't matter on that one at all, right, because it's already linear. I have x minus 2 squared, which is x squared minus 4x plus 4, x minus 2. So let's do the primary rational canonical form over complex numbers. I'll just do this block by block. Let's see, so notice that none of the blocks are bigger than 2. So we have 2 blocks here, 0, 1, and then 1 minus 2i for this one. And then I get minus I, little 1 block. We have 2 blocks for this one. 0, 1, 1, 2i. And then I get a plus I and a plus I. And then finally, I get a 2 block for this one. 0, 1, minus 4, 4, and then I get a 2. So there's a primary rational canonical form for this matrix over the complex numbers where you can break things down further. And finally, how about the Jordan canonical form? Now, the Jordan canonical form elementary Jordan blocks. Here are all eigenvalues. All your eigenvalues must be in whatever field that you're over. And lucky for us, the complex numbers are algebraically closed. So what do we have here? Well, this one's kind of akin to the primary rational canonical form. So basically what you need is you need the elementary divisors again. So back to this way, x plus one squared, x minus one, I. So now what you can do is you can make the blocks keying on the eigenvalues. Right, so let's look at the eigenvalue of negative I first. So first we get a two block. Get a two block here. A one block and a one block. Negative I, negative I. So that takes care of the eigenvalue, negative I. Now here, for the eigenvalue I, this corresponds to a two block. So this is I, 1, 0, I. And then again, you get one block and a one block in those straight linear terms. And for the eigenvalue 2, you get a two block and then a one block. Diagram showing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Good. And the Jordan form has its advantages too, because this one's always up triangular, right? So that's kind of neat. But of course, you can't use it if you don't have eigenvalues, right? So you have to go to a field where you have those eigenvalues. Everybody okay with that? So you feel like if I gave you the invariant factors, you probably kind of troll this out, right? Well, okay, so here's the next question. I mean, where in the world did invariant factors come in? Oh, let me give you kind of a, before I do that, let me give you a. So, how to get the invariant factors? I'm not going to prove it works, but actually it's not too hard to justify for yourself. Theorem. Let A set to set. Let A be an n by n matrix of K. So it's just your favorite n by n matrix of the field. Then the matrix of polynomials is equivalent via elementary row and column operations over the ring AX. And what I mean by that is this matrix here will have some x's in it. In fact, this is the matrix that you would use to compute the eigenvalues, right? You can invert x, right? You can invert any element of k, but, using elementary row and column operations over the ring kx, right? So you can't invert anything that's not a unit kx. To a diagonal matrix, so it's equivalent to a diagonal matrix. With diagonal entries. F1 divided F2 dividing Fn. And the non-constant Fi's are the invariant factors. This is called Smith normal form of matrix A minus X time. So in other words, you can figure out the invariant factors just by doing this. And the fact that you can actually get it into this form, it's easiest to use the fact that Kx is actually Euclidean domain. So you've got a Euclidean algorithm. For example, let me do a terribly simple one, and then pull the two. Suppose I have so what I would do here is find the Smith normal form of this. Well, I mean, just multiply this by x and add it up here, and that's going to be, and now, of course, I can use this column to take this out, right? And so now I just interchange the rows and I change the sign, there you got it. So this has one invariant factor, and actually it turns out that this is in fact a characteristic polynomial in this case. By the way, when you multiply, of course, all the invariant factors, you should get the characteristic polynomial. On the other hand, by the way, if this had been the matrix, if this had been the identity matrix, it would have been clear that you get 1 minus x, 1 minus x, and you're already done, right? Because it's already in Smith normal form. If you have this, then multiply this by x and add. Take this out. So now we get x squared minus 1. Again, characteristic polynomial. Let me give you one little more meat on it.
What were the operations we did here? How did we get that?
I used the 1 multiplied by x, take that out. So now I've got this form right here. Now use column operation, take that out.
Okay.
Right, so I literally use both row and column operations here. Let me see if I can get through this one. I might could. What if we have this matrix here? Uh, 1, 1, 2, 1. Three, 2. Or you could try 2, 7, minus 11, minus 2. Okay, so what if I wanted to do this by hand? So I get minus x, minus 1, 1, 0, 1, 1 minus x, 2, 1, 0 minus 3, 7 minus x, 2, 2, 7 minus 11 minus x. Okay, so the first thing I am going to do is I'm going to, so I'm gonna be kind of fast and loose with this because I have to be. I'm gonna use this one, take out this entire junk above and below. 2, 1. So I've already got 0, minus 3, 7 minus x, 2, multiplied by negative 2 and add. That's 2x plus 5. That's going to be minus 15. That's going to be minus x minus 4. And I'm going to multiply by x and add up here. And that's going to be minus x squared plus x minus 1. Yeah, times x and that. So it's going to be 2x plus 1. And that's going to be x. Everybody okay with that? Now, this 1, using column operations, sweeps this out. So at this point, I know what I've got after rearranging rows and columns. Do I agree with that? If I just put this up here, and so I've got a row, so I've got something in this form. So now I'm gonna reduce it down to 3 by 3 and see what I've got. So this is getting better. So now let's look at the 3 by 3 I've got in here. Minus x squared plus x minus 1, 2x plus 1, x, minus 3, 7 minus x, 2, and 2x plus 5 minus 15. 4. And at this point, I guess what I want to do is, just to make this easier, perhaps, I'm going to multiply it by half. And I'm going to use this one to take out stuff above and below it. So my middle row is going to be the same. It's going to be minus 3 halves, 1 half, minus 1 half x, isn't it? 7 halves. And finally, 1. And when I blast this above, multiply by x and add, I get 1 half x squared minus 3 halves x plus 1, that's 0. And I get minus x squared plus 5 halves x minus 1. And when I multiply by x plus 4 and add, I am going to get, right, 0 and I get minus 1/2 x squared plus 3/2 x minus 1 and 1/2 x minus 1. And again, I can sweep this out. Because I've got another one of the ones. So now what I have is 1 0 0 0 0 and the rest. And now this is more manageable. Because now what I have is this 2 by 2 thing. X squared minus 5 halves x minus 1. 1/2 x squared minus 3 halves x plus 1 minus 1/2 x minus 1 plus and minus 1/2 x squared plus 3/2 x minus.
Is that the top left entry a little different?
Maybe, let's see.
I think the first two signs are wrong.
I think you're right. Minus plus. There we go. That's better. Now I'm gonna sweep out the, just gonna make this look easier. Minus 2x squared plus 5x minus 2, x squared minus 3x plus 2, x minus 2, and x squared minus, let's see, I'm gonna put that up positive, didn't I? Minus x squared plus 3x. And notice there's something very obvious here to do, right? So what we'll do is we'll add this to this, and I get minus 2x squared plus 6x minus 4, 0, x minus 2 minus x squared 3x. 2. Now notice I'm going to divide out by 2, and this is actually minus 2 times x squared minus 3x plus 2, which is actually x plus 2x minus 2. So I'm going to get, I'm sorry, x minus 2x minus 1, and x minus 2. Multiply this one by x, multiply this column by x minus 1 and add. So I get x minus 2, x minus 1, x minus 2. Multiply this by x minus 1 and add. And this is x minus 2, x minus 1 squared. Right? And now, all I have to do is multiply this column by minus x minus 1 and take it. So basically, the invariant factors are x minus 2 and x minus 2, x minus 1. And this process always works. If you do it right, you can eliminate down to the invariant. Any questions on that? All right, I'm gonna give you some complicated matrices to do this week on the homework. Please, I don't want to see pages of this crap. get on MATLAB or whatever and ask it for the Smith normal form and just credit MATLAB and tell them this is where you got it, and I'm totally happy with that. Okay, questions? All right, well, I will see you folks on Wednesday.